organized by several chapters. This is an MTP microtheory and techniques chapter, and then propagation, aerospace and electronic systems, and geoscience and remote sensing. And now formally I'm going to read a short type CV of Dr. Martinis. This is the official one, it was sent by him. It says, Mario Martinis was born in Zagreb, Croatia in 1985. He received diploma engineering degree in electrical engineering from the University of Zagreb, Croatia in 2008. He was working as an engineer for dedicated course computers until 2011, and in 2011 he enrolled in a PhD program in electronics and telecommunications at the University of Rennes, France, and obtained a PhD degree in 2014. His research interest includes applied electromagnetics, antennas, metamaterials, microwave measurements, and microwave engineering. He is an author of several conference and journal papers on metamaterials and cavity antennas. That was the official part, and now I'll take the liberty and add a few words. Why? Because the point is that I was his supervisor during undergraduate study, and I really like to say that he was a brilliant student, one among the best students I ever had. And he was very diligent, interested in science and engineering all the time, and especially he was very able to defend his way of thinking. I remember very clearly that he was working finally a subject, finally a project that we've been arguing a lot of time regarding the subwave and metamaterial wave, and then my way of thinking was completely different than his way of thinking, and I must say that it turned out at many circumstances that he was right and his way of thinking was correct. So it is really indeed my pleasure having Mario over here, and I would like to welcome him. And Mario, now the floor is yours.
Thank you for this kind and thorough and very generous introduction. So today I will talk about my work that I did during my PhD thesis. We've entitled this presentation Metasurface cavity antennas, but I will tell you also what was the actual title of my PhD. So this slide is actually sort of a background slide. It serves as a reminder that there are many different types of antennas. But today, we will concentrate on cavity antennas, and these are antennas of this shape, for example. They're very simple type, just, let's say, a box or a cylinder like this. So out of all these antennas, today we're talking only about this type of antenna. And this slide was also an introduction to a more abstract title that was my PhD, which was developing characterization of metamaterials in cavities. And now, what are metamaterials? I will define during the presentation. And the main concern in my PhD was how to apply these metamaterials in cavities to the design of compact antennas. And by compact, I mean electrically small antennas. And I will also talk a lot about what this means. So my work was a collaboration between two institutes. This was the Institute of Electronics and Telecommunications in Rennes, which was a research institute, and an institute for defense applications in Saint Louis, ISL, where I spent the last year of my PhD developing these prototypes. So my talk is organized like this. I will first spend a few minutes introducing some important concepts needed for the rest of the presentation. Then I will talk about what cavity antennas are, how to analyze them, and how to understand them. And then I will talk about the bound on Q and maximum bandwidth, which actually means that I will be talking about the best possible cavity antenna. What is the best possible cavity antenna that can be built? And then I will show you a new design for cavity antennas that reaches this best possible scenario. And in the end, I will show you how to apply this new design of cavity antennas in certain applications and prototypes and experimental results we have so far that I have developed at ISL. Now, during my PhD, I was investigating two different types of geometries. This was the rectangular cavity geometry and the circular cavity geometry. But in this presentation, I will concentrate only on the circular geometry, because this is what applications demand. All the applications were actually involved in circular geometry, and all the examples I will give in this presentation will be concerned with the circular geometry. So, in the introduction, the first thing I want to address communication between devices. And for the communication part, we need antennas. Now, in the world of antennas, one of the simplest antenna form is the half-wavelength dipole. So, 100 years ago, the half-wavelength dipole at some frequency looked like this. It looked like this 50 years ago, and this is what it looks today. Now, there obviously is some kind of a problem here. So, don't get me wrong, I mean, antenna theory has been developed a lot in the recent, in the past century. There have been a lot of developments, but here I'm trying to make a point about the wavelength. And that's why specifically I said I'm considering the half-wavelength dipole. So what's the problem? The problem is that the antenna is a device that's supposed to emit electromagnetic waves into open space. These waves travel at the speed of light. And with these waves, there is an associated wavelength that depends on this speed of light. Now, the speed of light is a constant, so the half-wavelength size will always remain the same. The half-wavelength dipole will always be this size. So, there is definitely a problem of the size of the antenna compared to the wavelength of the waves it's supposed to transmit. Now, that being said, the size of the antenna compared to the wavelength can be miniaturized. But when you do this, when you miniaturize it compared to the wavelength, there is a major drawback. You have to pay the price in terms of antenna bandwidth. Once you do this, you increase the quality factor of the antenna, and this actually reduces the available bandwidth of the antenna. So this is a very important parameter, the size of the antenna compared to the wavelength. Now, in my PhD, we decided to work on antennas operating at 2.3 GHz, which corresponds to a wavelength of 13 centimeters. And this is this length. So this became the most important length in my PhD. And when I say that we developed compact or small antennas, I don't mean small antennas compared to my hand or this table or to my body. I mean compared to this length. This is the most important length, and when I show you some examples, you in fact have to see how small they are compared to the wavelength. So, while on the subject of wavelength, I want to tell you about the definition of metamaterials and what metamaterials in fact are, and what definition I am using in this PhD. So, first of all, what are materials? Well, materials are stuff made out of smaller stuff or objects or particles, and again, it's very important how small these particles are compared to the wavelength. Now, they can be as large as the wavelength, they can be smaller than the wavelength. Usually the description of such materials is very complicated. Or they can be much, much smaller than the wavelength. And this is a special case. This is what we usually consider as materials, because, for example, atoms and molecules are 1,000 times smaller than the wavelength of visible light. And this is why these materials that surround us seem like continuous materials, because the atoms inside are much, much smaller than the wavelength of visible light. So, why are we considering them as continuous? Is because once they are much, much smaller, instead of using the description that takes into account all these small particles and their position in space, we use something called homogenization. And this means replacing this complex material with something continuous and describing it with just two simple parameters. And this is the relative electropermittivity and relative permeability. Now, atoms are usually modeled as some small spheres, but recently people started to develop some new forms of atoms, let's say. Atoms of different shapes, sizes, geometry, and this turned out to be very beneficial for creating materials with some new properties, which are now called metamaterials. So these are materials that are engineered to have these different shapes compared to what normal atoms or small particles have. And they have new properties once you use something called homogenization. But the suffix what we use as a definition for a metamaterial is that these particles have to be very small or smaller than 1/10 of the wavelength, so that you can use the homogenization process and replace it with a continuous material. And this definition is not, I would say, exact in the scientific literature. There is not a definite consensus about this, but in most books and papers, this definition is the common one. And this is the definition I'm using in this presentation. And it's very important because at the end, I will claim that what I did has some connection with metamaterials based on this definition that if the particles are smaller than 1/10 of the wavelength, I can use homogenization and call this material a metamaterial. Okay, so now a word about patch antennas. Well, patch antennas are a simple form of an antenna. It's just a metallic patch. So here, a metallic patch over a ground plane and some material between the patch and the ground plane. And this material has some electric permittivity. This antenna works by exciting a wave that bounces off here between the patch and the ground plane, and here from the edges it radiates into open space. When you attach this antenna to an analyzer and measure it, you will get a curve looking like this, and what we are interested in is usually where this curve drops below this level of -10 dB. And we call this -10 dB bandwidth, because you see this curve depends on frequency. So -10 dB bandwidth is what I was concerned with in my PhD, and all the examples of bandwidth I will show you here will be of -10 dB bandwidth. One more thing about patch antennas is that when you use some different material between the patch and the ground plane, with, for example, a higher permittivity, what happens is that the wavelength inside this material gets shortened, and the consequence is that the size of the patch can also be reduced or miniaturized. Now this seems very important because we are dealing with small cavities, and it seems logical to use high permittivity material to miniaturize the patch enough so that it can fit inside a small cavity. But there is a drawback. Once you miniaturize the patch, it always leads to a smaller bandwidth. So, in conclusion, if you want to miniaturize a patch, you have to use a high permittivity material. But if you want better bandwidth, you need to use low permittivity or larger patch size, or use a thicker substrate, which summarizes into having a larger antenna altogether, or an antenna with a larger volume, which leads to larger bandwidth. Now this conclusion here is actually going to be repeated. I'm going to repeat it several times during the presentation, so it's very important. It's like a theme here. So now that I've talked about patch antennas, let's see what was the actual problem I was faced on my PhD. It was about placing patch antennas into projectiles or grenades, like this one. This is a patch antenna on the bottom of a projectile, and the projectile had some sensors inside. The purpose of this patch antenna was to transmit the telemetry data from these sensors back to the base station. And the frequency for this data transmission was around 2.3 GHz, or the wavelength was this. So these two other projectile pictures, they also have patch antennas inside, but they are not visible because there was a non-transparent layer here, but there is a patch antenna inside. And this cavity enclosure actually has some benefits. It allows for a miniature configuration of the whole antenna. It reduces background radiation. It isolates the antenna from its surroundings, suppresses surface waves, which is also a problem for patch antennas. But it further reduces the antenna bandwidth, and this is a big problem. Let me give you an example. So let's say we have a reference antenna, a patch without any cavity wall around it, and you simulate it and you get some certain bandwidth. As soon as you put a cavity around it, the bandwidth gets reduced. But the real problem is when you want to use a very small cavity. Then the bandwidth gets significantly reduced. So our question is, what is the maximum achievable bandwidth for a cavity of a given size? And will this be enough for our applications? And is it even possible to create these very small cavity antennas? So we decided to investigate several cavity sizes, and here this is cavity size in diameter, so this diameter of the cavity. And compared to the wavelength, which is the actual parameter that's important, we were interested in sizes that are 0.15 in wavelength in diameter, or a quarter of a wavelength, or a third of a wavelength, or this is one larger, 0.38 in wavelength. So several different cavity sizes. We wanted to investigate them and find out what is the maximum achievable bandwidth. the thickness of the cavity inside, so the height of the cavity, was also restricted. This turned out not to be such a serious constraint. And we were looking for a patch-like radiation. So this means that the antenna is radiating perpendicular to the aperture of the cavity. So, let's talk more in detail about cavity antennas. The simplest form of a cavity antenna is just a hole in the ground plane. So, a hole in some large ground plane. And there is a simple model of this antenna, which is a transmission line model, which models the cavity part with this transmission line. Why? Because this cavity can actually be regarded as a small portion of a waveguide. The waveguides have a fundamental mode that can propagate inside, a wave that can propagate inside the cavity, and this transmission line models this propagation inside the cavity. Now, this part of the model models what's happening outside the cavity. So when the cavity is resonating, it's radiating some waves into open space, into infinity. And this radiation is modeled by this resistor, or radiation loss. But when it's resonating, there are also some currents in this ground. Currents produce magnetic fields. So this energy stored in this magnetic field is modeled by this inductor here. This is actually modeling the near field of the antenna. And I know that this still may seem very, very abstract, although I say it's simple. So I have an analogy here. And I hope that you all played with this as kids when you had a bottle and you did this. This is a cavity resonance. And I hope you all remember when you were kids, if you filled it up with more water, you can change the frequency of the resonance. So if you put more water inside, you will have a higher frequency. I inserted a lot of water here because I wanted a very high tone. So what's the cavity here? This part of it is filled with air is the cavity, and obviously here you have an open aperture. When I blow in it, what you hear is actually the cavity resonating. So this is an example of a cavity resonance, and what I have on the screen here is just an electromagnetic analog of this bubble. But now I will have to put a little more mathematics into this. How do we analyze this in the electromagnetic case? So first of all, the cavity part, the transmission line, has to be modeled by some input admittance, the inverse of impedance. And you have to write some equations, these are the expanded equations, and the only thing that's important in these equations is this cotangent function, which visually looks like this. For a cavity that's filled, the volume of the cavity is filled with a permittivity of 10 inside. And this is the dependence on the input admittance on height, so on this height of the cavity. So what we see here is that for very thin cavities, the input admittance is inductive. But as the cavity gets longer, height increases, the input admittance turns from inductive to capacitive. This is very important. And if you change the volume, what's put in the volume, if the permittivity is lower, also the input admittance changes. For the case of very low permittivity inside, 3.6, this waveguide turns out to be under cutoff, which means the input admittance is always inductive. You see, it's always negative, so it means it's always inductive. On the other hand, this part of the model gets described by some aperture admittance, which looks like this in the analytical form, very complicated, and it's very complicated to derive this formula, but visually it looks like this. It tells you what is the aperture admittance depending on the size of the cavity. So this is depending on this diameter, how this aperture admittance change, and I have noted here what is the aperture admittance of the cavity sizes I'm interested in this PhD. I was interested in this PhD. So now that you have all this, you see that for all these cavity sizes, the aperture admittance was always inductive. Once you have all this, you can put it into an equation that determines when is this cavity going to resonate. But I want to give you a visual demonstration of how you can understand this equation here. So for an example, if you take a cavity that's a third of a wavelength in size, you can see that you'll see, okay, here I am at this curve for permittivity of 10 inside, and the cavity should be around 15 millimeters high to achieve resonance. If the cavity is filled with permittivity of 10 inside. If the cavity is filled with permittivity of 6, I will need something like 26 millimeters of height for the cavity to achieve resonance. And only at this height will the cavity resonate. For the permittivity of 3 inside, there can be no resonance because this part, the cavity part of the antenna, will be always inductive. So before I go to the next slide, where I will actually show you these examples, so what I said, 15 millimeters here and 36 millimeters here, will be shown in the next slide also. Before I go there, I also want to mention that this model is good for describing antennas in a large ground plane and also in a small ground plane or a finite ground plane, like, for example, what we had in our applications. So you have the aperture here, but the ground plane around it is finite. And this model can describe these antennas, but in this case, it's more approximate. What I had before for an infinite ground plane was completely analytical. When I have a finite ground plane, it's approximate. I have to use simulations to get this aperture impedance. This is the only difference. So, now that I described how to analyze this with admittances, once you have all the admittances, you can calculate the quality factor of the antenna with this formula involving only the admittance part. And you can calculate the bandwidth of such antenna because there is a simple formula connecting bandwidth and the quality factor. They're inversely proportional. And in fact, this factor, 2/3, you can immediately get the minus 10 dB bandwidth, which is what we are interested in the applications. But there is one important thing about this formula, and that is that we have to know its assumptions. The assumptions for this formula to work is that we are dealing with a single resonance antenna and that the values of this Q factor are very large. This will become very important later. So, as I said, for a cavity filled with permittivity of 10 inside, on the last slide we saw that the cavity should be 15 millimeters high, and with this formula you calculate the available bandwidth for such an antenna will be around 85 megahertz. For a cavity filled with permittivity of 6 inside, it's 26 millimeters, and you have some other bandwidth. Permittivity of 3 inside, it doesn't work. This is about the simplest form of cavity antennas. Now, I will jump immediately to the case of having a patch at the aperture of the cavity antenna. And just to have an analogy again, this was the simple cavity antenna, and here I have a patch that I can put on top of my cavity. This is actually also a cap, but it has a hole inside, through which I can blow. So now try to remember the frequency of the normal cavity antenna and the one with the patch. So I hope you noticed the difference in the frequency. What does this mean? If you remember, the frequency was lower with the patch. If I wanted to get the same frequency, I would need to put more water here and reduce the size of the cavity to enhance the frequency. So it means that if I want the same frequency of operation of this cavity antenna, I can play with the size of the cavity or what's happening at the aperture. So I have two variables now. And this is exactly what's happening with patch antennas here. Now I can change the height, and as I change the height, I also need to change the size of the patch and aperture, and I can have a cavity resonate for each height. And these are simulation results, and we did these simulations for different types of permittivities inside the cavity. So this is for the lowest permittivity, and we got these simulation results, which are interesting for several different reasons. First of all, here in for thin cavities, you can see this red curve for high permittivity inside. It's the bandwidth. The bandwidth for these antennas is lower compared to these antennas with a lower permittivity. This is what's expected from patch antennas, what the books say. But then there is this region here, where you can see that this red curve, corresponding to this antenna, for example, has, it says that this antenna has a larger bandwidth compared to this green curve for this antenna, and predict, because here the patch is larger compared to this. So here the patch antenna is miniaturized, but the bandwidth is larger. Completely unexpected, I would say. This confused us a lot, and it demanded some explanation. Another confusing thing was this bandwidth bump in this curve, which occurred for no particular reason. But the most important question
is this numerical simulation?
These are numerical simulations. This is CST. So the most important question we were concerned in is, did we reach some maximum bandwidth for this cavity size? Is this the maximum? Is this the maximum? What is the maximum? This is what we are mostly concerned about. But to answer all these questions, I first started to model the antenna by considering the model for the simplest cavity and trying to enhance it somehow to see what happens when you have a patch inside. So the way I did it is I looked at the cavity with the patch and I said, well, okay, so here at the aperture I have this patch. So when it's resonating, then here between the patch and the wall, I will probably have some electric fields when it's resonating. So I'll model this with the capacitor. On the patch metallization itself, I will have some currents. Currents produce magnetic fields, so I will model it with an inductor. And here on the bottom again, I will have some electric fields, so it's modeled with a capacitor. So the enhanced model looks like this. I just added this part for the patch. And this model now has more variables compared to the simple cavity antenna. So except for the height, we now have this capacitor and an inductor. And when I played with this in Mathematica, analytically, I got results looking like this. And I said, great! Well, look at this. I have this bandwidth inversion phenomenon. This red curve is above the green curve. I managed to predict what I got with my simulations. This is great. It means the model can explain the phenomenon I'm observing. But then I started to play with the value of this inductor here. I started to lower this value, and I saw, bandwidth increased. I lowered it even further. It was better. I lowered it even further, and I saw, wow, I'm starting to lose this bandwidth inversion phenomenon, and the bandwidth is much higher. Obviously, this inductor is not very good. Why don't I get rid of it and just put a capacitor? And I got the best possible result, but I saw, okay, so the low permittivity value is on the top. So what if I lower it even further and put just air inside the cavity? Permittivity of 1. And this turned out to be the best possible result so far. So it's just rising to some level and then just leveling off after a certain height. It's just a constant value. And this was the aha moment in my PhD when I said, wow, maybe I just have to put a capacitor at the aperture. And this is something we will get back to later in the presentation. But before then, I have to explain the other phenomenon we saw, which was the bandwidth pump. For this, and the professors are eager to help. There is meetings, they talk a lot of each other, but weeks pass by, no results. And the farmer is very, very worried, and he's losing his chickens, no eggs, no nothing. Finally, after months, a physics professor comes along, and he says, I got it! I have the solution! But the solution works for spherical chickens in vacuum. And this is exactly what Chu did for antennas. He found the solution for the best possible antenna, but it works for spherical antennas in vacuum. Nevertheless, his result is very important, and it was the state of the art for 60 years. So he did it by crunching a lot of mathematics, spherical harmonics, blah blah blah, and in the end he developed a very simple formula that's now called the Chu bound. And the way to understand this formula is by looking at this radius here. So this is the radius of the sphere to the third power. And in fact, if you have a sphere and you have a radius, you maybe remember that the volume of a sphere is connected to the third power of the radius. So this is in fact volume, and this k, the wave number, in fact turns this part into something I can interpret as electrical volume, meaning volume compared to the wavelength. So the minimum quality factor of such an antenna is inversely proportional to the electrical volume. Or in fact, we can say this bandwidth is inversely proportional to the quality factor, that if you have a larger volume, you will have a larger bandwidth. This is a very important general conclusion. But as you may first slide with a lot of antennas, most of the chickens are not spherical. So, this was the state of the art for 60 years until this person came along, Mats Gustafsson from the University of Sweden. And he very recently published a paper about physical limitations on antennas of arbitrary shape. And he said, now we can analyze any shape. And the way to do this is by analyzing how this shape scatters electromagnetic waves. So you make some scattering function or mathematics again, but he says this scattering is not important at any frequency. What's important is to consider low frequency limits or frequency zero, meaning we have to consider how this object behaves in a static field, in a static uniform electric or magnetic field. What happens then is that this object polarizes. Some charges get separated by this object and it produces some of its own field which disturbs the uniform field. The way to describe this is by a number called polarizability. It's a measure of how much these charges get separated on this object. And this number becomes the most important number in the new formula for the minimum quality factor of antennas. The formula also involves something called directivity, which is an important parameter of antennas, something called absorption, but the most important thing is the polarizability. And it's very general. But there is a problem, that is that Gustafsson's approach will never tell you how to excite the antenna, how to actually make this antenna, only what's the best possible scenario. So to make an antenna, you always have to attach some cable to it. And do you attach it like this? Do you attach it like this? Or like this? You don't know. This is a completely different problem, not addressed by this theory. But nevertheless, this theory is very general. So general that I was able to apply it to cavity antennas with one restriction. The restriction is that it worked for cavities in a very large or infinite ground plane. So I started analyzing this theory using this formula, and I would like to tell you how I developed this, which is the actual polarizability of cavity, circular cavity antennas in the ground plane, but in fact this derivation takes around 30 pages of pure mathematics in my PhD, and it took me around a year to develop correctly. So it's very, very complicated. But once I had this, I was able to write the complete formula for the minimum quality factor of circular cavity antennas in an infinite ground plane. And this formula has two parts. One part that takes into account the height and geometry of the cavity, and one part that's similar to the tube bond. It has this electrical volume here. So very similar to something we saw previously. If you punch in all these numerical values here, you get something even more similar, or large heights, where you see this is very similar to the tube bond. Except that in the tube bond we had a factor 1 here, and now it's a factor 10. But this formula is exact for cavities, and not for spherical antennas. Once you have the Q factor, you can again get the bandwidth from the Q factor. And visually, what these equations gave me is predictions for maximum theoretical bandwidth. It looked like this. If you remember, my examples were for a cavity size of diameter of a third of a gun. So this curve presents the predicted maximum for a cavity of this size that can now be compared to the simulation results I showed earlier. Okay, I also put some quality factors here, but what's important is that now that I had these results, I can compare them to my simulation results. I made simulation results for patch antennas in different sizes in an infinite ground plane. These are the simulation results, and on top of that I applied my theoretical results, and this is what I got. In all cases, this red curve, which is for the theory compared to simulations, in all cases it's above my simulation results. What does this mean? It means that patch antennas are not good enough. They do not reach the predicted maximum bandwidth. Something better can be done. But there is one more thing, and that is that when I looked at the Gustafsson's approach, and I saw how complicated it is, it's so abstract. But again, it gave me this proof of what is the maximum bandwidth. I remembered that there was this transmission line that I also investigated that gave me best results with the capacitor. And I say, let's compare these results. And I got almost a complete match. with predictions from this transmission line model. And this is a fantastic result, because this transmission line model is simple, it's understandable, it gives me the same predictions as Gustavson's approach, but it's no proof, it's just a model. This approach gives me the proof. But this transmission line model shows me how to actually make this antenna. What I have to do is just place this capacitor at the aperture, and I will be at the maximum theoretical bandwidth. And one additional thing to this is that this model is extendable to cavities in a finite-sized ground plane, which is a bit approximate, but if you remember, the Gustavson's approach is only for cavities in an infinite ground plane. With the traditional model, I can make predictions for a finite ground plane. Antennas which are what we use in applications. So, I have answered all the questions. The only thing that's left is to build these antennas. So, what needs to be developed is actually this capacitor at the aperture. And I knew that the patch at the aperture is not a good choice. What's the problem is the current that flows inside, that flows on this metallization and produces a magnetic field which gets formed by the inductor, so I need to break this current somehow. So I started breaking up this patch into smaller and smaller pieces to eventually reach some ideal distributed capacitor, which is actually just a capacitor. So this is how it looked in the end. And this is where I start claiming that this is in fact a metamaterial. Why? Because these elements of this surface here, of this object here, these elements have to be much, much smaller than the wavelength. It turned out that they have to be smaller than 1/13th of the wavelength, and as you remember, the definition was that if the elements are smaller than 1/10, we can use homogenization and call it the metamaterial. In this case, the homogenization is replacing this complicated object with a simple capacitor. That's homogenization in this case. And these elements are much, much smaller than the wavelength, so I'm claiming that this is a metamaterial, or specifically a metasurface. One thing that remained to do is the excitation of this antenna. This was the harder part of creating this antenna, because there are many different types of excitations. Some turned out not to be so good, some turned to work well, and in the end we decided to use this excitation type for mostly practical purposes. It was the easiest to manufacture. It used a correction cable that went all the way up to the aperture and had a small transmission line here that capacitively coupled to the metasurface at the aperture. So, now that I have everything, I will show you the final design of the antennas we developed. It was a cavity with a thin, very thin layer of substrate that held the metasurface because it cannot stand in air. And this substrate was glued to the cavity wall by some glue, and the volume inside was filled with some low permittivity material, ideally it's air. On this transmission line, from the top looks like this, it's slightly tapered. And when the cavity is very small, I use this design, which has a multi-layer surface design, because for example, for very small cavities, like this is a very small cavity, the necessary capacitance value is very large, so I have inserted more layers here to increase the capacitance value. This presents some problem that will be visible in this slide, where I compare the theoretical predictions and my simulation results. The black curve is the theoretical prediction, and the dots here are simulation results for cavities with these metasurfaces at the apertures. First of all, you can see that as the size of the aperture gets larger, the number of elements change. So this is because, as I said, the element size should be 1/13 of the wavelength. So if the aperture is larger, then more elements fit inside. This is the reason why there are more elements for a larger cavity. And for example, here, for the smallest cavity size, you see that we didn't really reach the maximum. And the reason for this is because I had to use this multi-layer design. The problem is that in this case the capacitor is not strictly at the aperture, but effectively it's somewhere below, because it's a very thick capacitor. This has a result that it's very hard to reach the maximum. And for these cases, I got very good agreement between theory and simulations. maximum, the theoretical maximum. The reason why I got this is because the formula I used is only approximate, and the assumptions for this formula started to be invalid. This is no longer a single resonance antenna. There is in fact a resonance at the higher frequency that starts affecting the lower frequency, and it messes up the assumptions of this formula. And also the Q factor values are coming very low. For the problem with these large cavity antennas, I will have a concrete example later in the presentation. But because this formula is approximate, I have this discrepancy between theory and simulations. For the finite ground plane cavities, I made again a lot of simulations. I got some good results and some discrepancies, which are again for the same reason, because these are no longer just a single resonance antenna, and the Q values are very small. But in fact, these were great results, much larger bandwidth compared to the patch antennas that were used so far. So once we had this design, we have the theory. Let's talk about the applications. For the existing projectiles that were used with the ISL, instead of these patch antennas that were used so far, now we can use our Metasurface design. So compared to this patch antenna, now we can use this Metasurface design. The benefit is that we have larger bandwidth, which can be used for more data transmission, or the manufacturing process becomes more tolerable to inaccuracies in the process of manufacturing. So we had some prototypes of first patch antennas, and we measured for this patch antenna 52 megahertz of bandwidth. This is a patch antenna filled with permissive 6 inside. Here it was a patch antenna filled with permissive 10. We got 60 megahertz, and with our Metasurface design, so this is this antenna in fact, we got 90 megahertz of bandwidth, which is 50% more than what we were able to achieve with the patch antenna. So, and all the other characteristics, the radiation pattern and gain, remain the same. We have a benefit in bandwidth exactly what we wanted. So this is for already existing projectile applications, and for a very small projectile, which is something that was so far impossible to do at ISL Institute where I work, because patch antennas in very small cavities were impossible, because once the cavity size is very small, the patch and the aperture fills almost the entire surface, and you can actually not manufacture this antenna to work properly. You can try to do this multi-layer approach to reduce the size of the patch and the aperture, but you lose bandwidth. And with the Metasurface design, you can have the antenna working, and it will have a larger bandwidth. So in fact, the Metasurface design offers a wider bandwidth compared to what's possible with patch antennas, even for smaller antennas. And we made some prototypes. So this is a 20mm prototype, which was considered not manufacturable before. Now with the Metasurface design, it's manufacturable, and it works. This is a comparison between a simulation and measurements. And we said, okay, now that we have this very small antenna, well, maybe we can build even smaller antennas, and we built a 16mm diameter, or 0.12 wavelengths in size antenna, and this one also worked. We had a slight frequency shift, but it's a demonstration that this is in fact possible, and it's a completely new ability for ISL, and it can be used in new projectile applications for projectiles or with very small calculus. Now, I can just say that the manufacturing process of these antennas is the same as for patch antennas, so nothing new has to be done, and okay, there are new applications involved now. This is something completely different now. Instead of the small cavities, I'm considering now larger cavities, and I unfortunately have just an example for the rectangular cavity. So looking here, there's a rectangular cavity with a Metasurface at the aperture, and what you see here when the cavity size is large, for example 0.5, half of the wavelength, there are two resonances. This is what I was talking about. The second resonance starts affecting the lower resonance. The formulas I used could account for this resonance, but it cannot account for this resonance, and the bandwidth broadening effect between them. This is why I have approximate results for discrepancy between simulation Because once you have this broadening, bandwidth broadening effect, you can compare this to alternative antennas, for example, patch antennas, and see that this Metasurface design again has a benefit in bandwidth compared to classical antennas or antennas used so far in practice. I also investigated some antenna arrays, but I will just skip through this. This is something that's maybe interesting for future work. I also investigated what happens with magnetic materials in cavities, and it turned out, also just quickly, that the bound of Q can be much lower if you use high permeability materials inside the cavity. But this result is purely theoretical at the moment, because there are no high permeability materials at high frequencies, so this is maybe for a distant future. At the moment, it's just academic. But with this, I would like to conclude. So I've shown you my theoretical contributions. So an explanation of how patch antennas in cavities work, explanation, determination of the bound of Q and the maximum theoretical bandwidth of cavity antennas theoretically, and the model that explains how to reach this bound, and from a practical perspective, the design of antennas that can actually reach this maximum bandwidth. For the applications, this is more connected with ISL, we can now create antennas with a wider bandwidth, or antennas with a smaller cavity, which can be used for small caliber projectiles. In the future, we can think of a better manufacturing process, not to have frequency shifts because of manufacturing inaccuracies. Some high acceleration tests should be done for firing these projectiles with Metasurface antennas, but good results are expected because all the same materials are used. The broadband cavities can be manufactured because this is also an interesting area of research because it can replace some existing types, for example, stacked patches, as I mentioned, and the design of antenna arrays. So, in my PhD, I had a lot of help from many different people, but they are not in the audience at the moment. And this, I would like to just end my presentation and thank you for listening to me and enduring me for 50 minutes. And I hope it wasn't too boring and you didn't fall asleep. And now we can talk about some questions that you may have. Thank you very much. E sad, iz simulacije.
Ali tu su pretpostavili savršene vodiče.
Mislim da je u ovom slučaju savršeno vodič, da. Ja sam htio, kad sam uspoređivao ove stvari, ja sam htio što sličnije uvjete. Znači, ja mislim da čak možda u ovoj simulaciji može biti 200 gubitaka skroz. Jer mene zanimala je usporedba u istim uvjetima, usporedba širine pojasa za ove antene. Vidio sam to, mislim, dijagram zračenja je prvo, mislim, skoro isti, znači isti, jedina širina pojasa veća. Znači, ova antena je to bolja, što tiče širine pojasa.
Da, to bi bilo zanimljivo vidjeti kad se stvari materijali vrsta, slučajno nema to nekih efekata tipa ono, što su mali metalići, da tu nema puno gubitaka i nešto
u ovom slučaju ne bi trebalo biti, ali to jednostavno nije bilo vremena na kraju za to je za neki budući.
Da imamo čistu situaciju i još uvijek nije sasvim jasno.
Da. Zato imamo bar za ove antene prototipove. I tu ima gubitaka i vrlo su bitni.
Da li postoji maksimalni kapacitet koji bi bio idealan pri takvim antenama?
Znači, granice na maksimalni kapacitet ne postoji. Kapacitet ovisi... Kapacitet se regulira sa ovim ovdje rupicama. Znači, smo ovaj gap, kako to prevede. Znači, prorez ovdje. Što je manji prorez, tu, što je manji taj prorez, to je veći kapacitet. Teoretski mi možemo razmišljati da taj prorez bude infinitezimalno mali i znači kapacitet bi bio velik.
Sam bi onda zaokreovali se, da imamo mi više rezonantne frekvencije.
Nema, mislim, da bi antena razbirala, mora biti baš određena razina kapaciteta. To ne smije biti prevelika, niti premala, mora biti određena koliko je potrebno za rezonanciju na određenoj frekvenciji. Ne znam, kaj si?
Prvo, ja stvarno sam impresioniran količinom materijala što se napravi u doktoratu, a i prezentacija mi se jako svidjela, sve mi je žao što predavanje je završeno.
Možeš ti nastaviti.
A sada pitanje. Ok, znači, sad piše za ove antene koje si izradio, pretpostavljam da će napraviti simulaciju, pa ste napravili zbilja i mjerenja. Sad ono stekiranje, znači nekoliko pečeva jedan iza drugoga, kako se ponašao u praksi, znači mjerenja, kako su bila mjerenja tih antena, jer pretpostavljam da ste koristili neko ljepilo za ljepljenje pečeva. Ja osobno bi koristio recimo epoksi, koji ima valjda katastrofalne svojstva na visokim frekvencijama, kako se
Znači,
snašao?
to ljepilo je najveći problem. Da, i sad ljepilo koje oni koriste u ESL-u koji su izrađivali antene, to je tajno. Ja ni ne znam kako se koristi, da. Ali se koristi to neko bijelo ljepilo.
Cartofix.
I ljepilo ima katastrofalna svojstva, ima jako velike gubitke i što je antena manja, to je i to ljepilo u ovom prorezu između materijala i šupljine, to je to bitnije. I ti gubici su sve bitniji i da koristimo bolje ljepilo i antena bi samo bila bolja. To je uništavalo hrpu rezultata, da. Imamo, ne znam, za ovu najmanju antenu, samo zbog tog ljepila efikasnost je 13%.
Kako se dijeli performanse ljepila, mislim, jeste ga mjerili?
Da, ljepilo je mjereno, ali to je aproksimativno mjerenje, ja rekao. Ja sam zapravo na kraju vidio koji je rezultat mjerenja s antenom i onda sam po tome naštimao u simulaciji da dobijem isti rezultat u širini pojasa kao i u mjerenju, pa da procijenim koji je stvarni gubitak u tom mjerenju. I to je ispalo neko veliki gubitak je ispalo.
Sljedeće pitanje.
I zato kažem kao, ako uspijemo naprijediti proces izrade, bit će i bolje antene. Ali dizajn je isti, samo je pitanje izrade antene.
Kako bi se držala tako ista frekvencija, ona je najbolje naštimena, na kraj naštimena. Što, dakle, moglo bi se staviti puno ovih komadića, ali to bi značilo vjerojatno da lakše otpadne na komadić, dakle manje robustna antena, tako nešto. Mislim, koji su nekakvi praktični limiti, kako je rekao?
Ne.
Mislim, ti si vjerojatno proširio spektar.
Ne, znači unutra eksplodirava barut i slične stvari, postoji šansa da se ošteti naravno antena, ali zato se na nju stavi još jedan sloj koji štiti. Znači, nema opasnosti da će se uništiti antena. A što se tiče tih komadića koji broj je optimalan, ispada da ako su komadići manji od 1/13, ne treba stići puno manji komadića. Znači, to je dovoljno da antena radi dobro.
Ali onda možemo staviti više komadića koji je veći od...
Ako je antena veća, onda ti stane više komadića i mora imati više. A za manju antenu ih mora biti manje, znate, na ovoj slici. Tu, znači za vrlo malo, prošle je bilo dovoljno 2 komadića. Malo veću 3, i ne znam, za ovu jako veliku je bilo trebalo potrebno puno komadića. Ali u svakom slučaju, u svakom primjeru, je komadić velik 1/13 normalne duljine.
Ali možda se sam još pitanje, dakle, to nisam tehničar i tako, ali vezano s ljepilo, koje su točno njegove svojstva koje smetaju? Je li neka magnetska, električna ili...
Da, električna svojstva.
Dakle, voditost.
Mislim, kao i svaka, kad pričamo o gubicima, znači da se nešto zagrijava. I sad antena radi i dio energije, umjesto da se izrači van, se troši na zagrijavanje tog ljepila. To je loše. Kad kažemo da je gubitak, to znači da će se zagrijati dok antena radi. Eto, i to je onda gubitak. To nije snaga koja je izračena van.
Glupo pitanje, znači ovo su mjerenja rađenja čistih antena. Kažeš nalaze se u projektilima poslije toga koja se spaljuju iz topova ono. Da li su rađene nekakva mjerenja unutar tih projektila, da li se smanjuje njihov bandwidth, da li se smanjuje njihova snaga koju se pokušu dobiti?
Da, isto nije bilo vremena na kraju napraviti pucanje tih projektila.
Dakle, tu se radi o jednoj šuplji rezonantnoj i radi se o zračenom slobodnom prostoru. I ovo u stvari nije ništa drugo nego rezonancija.
Tako, LC je pitanje drugo.
Dodaje se kapacitetna struktura da bi dobio rezonancu, da ga spremi to unutarnji faktor, vanjski i tako dalje. Kada se ovo usporedi sa pristupom, recimo, Siemens Vipera sa ovim visoko impedantnim površinama, koje su sličnosti i razlike?
Da, to je super pitanje jer sam ja baš imao odjavak gdje sam uspoređivao sa time. Znači, koja je radila? Siemens Viper je radio površine koje su služile kao površine ispod nekakve antene. U ovom slučaju je površina glavni element i, samo da nađem, Siemens Viper koristi one mašine strukture. Ovo nije mašina, ovo je samo reactive business surface.
Fizika.
Fizika je što se događa iza te površine. Iza te površine je valovod koji je evanescentan. Mnogi ljudi su me pitali kako usporedno sa FER-ovim rezonatorom. Ovo nije FER-ov rezonator, zato jer nema rezonancije u ovoj transmisijskoj liniji. Znači, ovdje val samo se gasi. I zato to nije FER-ov rezonator i nije niti takva vrsta površine, jer u takva vrsta površine isto tako ova linija iza površine igra veliku ulogu i bitno je kao koliko je duga. A kod mene, nakon nekog vremena, je uopće više ima nikakvu ulogu. Da se možemo riješiti te šupljine, to bi bilo najidealnija situacija. I to se zapravo i može, ali samo s magnetskim materijalom. Znači, baš je različito od Siemens Vipera. Način na koji se koristi ta površina u Siemens Viperu.
Ok, i tako kratko zadnje pitanje. Dakle, vi ste pokazali da čuvo limit koji svi koristimo vrijedi naravno za sferu i da je, ajmo reći, manj. Mnogi ljudi tvrde da mogu ići ispod. I sad me zanima vaše iskustvo nakon 3 godine na to. Da li se možete ići ili ispod njih?
Ne može se ići.
Ne može se ići.
Ja znam da radim od Zirokovskog, ali to je sve takva teoretika nekakva meni, ako se on izbaci neki fizikalni zakon i onda može ići ispod čulovi, ali inače ne. U realnosti ne može. Može se doći vrlo blizu, znam za imam primjer od vas, primjer koji su najbliže došli u čulovoj realnosti.
Dakle, ne možemo prirodu prevajati.
Ne.
Okay.
Ovo je primjer da se metamaterijalno može doći do granice. Ne može se preko granice. Ali to je već napredak jer se do sada nije moglo doći do granice. A sad se konačno barem u ovom slučaju smo došli do granice.
Da li još neko ima bilo kakvo pitanje, komentar? Ako nema, ja bih se zahvalio naravno Mariju, svima vama koji ste došli, još jednom čestitali, zatvaram ovo predavanje.